Well, good afternoon, everyone. Are you having a good time here at Scala Days Berlin? Yep, good. Yeah, I love Berlin. It's a lot of fun. The European Scala Days there's a great vibe about them, so it's quite an honor and a joy to be here. I'm going to talk about something today around the idea of microservices and in conjunction with the notion of fast data. And we'll talk about what I mean by that and what microservices are and fast data are to kind of level set ourselves. And then after we do that, we're going to take a look at a design for a production system that would be implementing these things and what it might look like. So a little bit about me. I started out many years ago as a VP of engineering, and I liked TypeSafe so much that I left that position and joined them as a senior software engineer. I was on the Insider monitoring team for 2 years, and now I am a systems engineer, and I work still with engineering, but also with our clients too, designing and helping them understand how to build really large, robust distributed systems. So I've been building these systems for about 10 years, and it's been delightful and horrible all at the same time. There's a lot of crazy things going on, but when I ran into it about 12 years ago, I realized the design or the monolithic style that I was used to was not going to work. I was in the energy industry, and the volume of data that we were using was enormous. So that led me down this path, and took the opportunity with some of my friends, Sean Walsh and Brian Hanafy, to write a book about it, using the reactive notion. It's kind of a sister book to Roland Kuhn's and Jamie Allen's and Brian's book. Theirs is more design pattern based. Ours is more real world implementation. And that's my Twitter and GitHub accounts. So, you know Lightbend. Anybody not heard of Lightbend? We're kind of the people behind Scala, akka, Play, Lagom, and what we call our fast data platform. And one of the things that started this entire process was this whole idea behind a reactive and how can we build systems or business systems, and not just business systems, but systems that would be able to stay up and run, because the demand that customers want are 100% uptime, pages to load in under a second, for everything. So the idea of reactive is ready to respond to an input or stimulus. And then, of course, we have the Reactive Manifesto, which is kind of like a superset of all this. It's a very high-level abstraction to think about, and it doesn't necessarily have to apply to just JVM or Scala and akka-style applications. It can apply to other things as well. And to date, it has over 20,000 signatures. So this diagram, I think, is really important because it kind of gives you, and we've all seen it, but I think one of the things that we miss sometimes, or at least I missed for a while, was the arrows, right? The arrows are very significant. So at the top, you have responsiveness. We all know what that is. We have to respond. It doesn't matter what's going on. The customer wants a response. In order to facilitate that, we have to be elastic. We have to be able to scale in and out and up and down. And we have to be resilient. We have to self-heal. So you'll notice that the arrows between resiliency and elasticity are bidirectional. So in order to be elastic, sometimes we have to do something that is resilient, and in order to become resilient, sometimes we have to do something that's elastic. So one of the ways we can be resilient is to expand horizontally or scale horizontally. And ultimately, all this stuff is driven by something called a message-driven architecture, and that applies directly to how we're going to define microservices. And then you'll see the two pillars, elasticity and resilience, support responsiveness, and message-driven response supports them all. So a little bit about us. We have open source offerings, Play, akka, Lagom, etc. Those are our core open source offerings. I'm sure many of you are used to them. Scala is also one. And we have these different concepts that we have embedded into something that we call our reactive platform, or which contains not only our open source, but also our commercial offerings. So things like monitoring, telemetry gathering, insights, split brain resolver for clusters, etc. Something new that we've been working on and is kind of related to our talk today, a big chunk of it, is this idea behind what we call our fast data platform. And essentially the idea is when you're integrating things like services or microservices and you want to take advantage of things like streaming data, it's a rather complex setup. How do you do it? Where do you do it? And that's going to be the core of our talk today. But in this particular product that we have, we integrate all that stuff that you see on the screen. We're integrating other stuff as well. We provide support for it, etc. And this is kind of like a future of where we see general application design heading. Okay, enough of that. We are going to talk about several topics, and I'm going to walk through a discussion about each one of these. So one, obviously, is microservices. Another one is called promise theory, which is core to, or we believe is core to microservice design. Event sourcing, CRUD, right? Relational models, relational state models. Fast data in and of itself. And one that I'm particularly fond of, feedback control. Feedback control is an emerging pattern in technology and software design that really stems from regular mechanical design and so forth. But it's an interesting topic in software design, as we'll see. So first of all, microservices. You know, everybody has a different definition for them. One of the common definitions is this: the idea that you're building systems that are going to join together in some fashion to represent a context for an application. And these systems, one of the advantages to doing it this way is you can have multiple teams that can be separated physically. They can design, develop, and manage and deploy their applications independent of one another. And I think that's a great definition, but I think there's a better definition, and it's this one: a system of autonomous collaborative system, or distributed services. Autonomy, the Greek word, it essentially means self-governing. So the idea is when you're designing a system, your microservice, you want it to be self-governing, i.e. it stands on its own regardless of feedback or whatever's going on and around it. And this is one of the key components behind Reactive. So some of the key concepts, we'll talk about this next, but is think in promises inside your design as opposed to obligations. Another one is keep your services small, hence the name micro. Who here likes functional programming? Right? Why do we like it? Because it's pretty straightforward. It's mathematical. If you put the same input, you will always get the same output. It does one thing. I've seen people write functional code that does like 6 things, and they use, you know, strange symbols that nobody can read except for them. And the point is that it's not functional because it's doing 6 things within it. So, right? So you keep it small. The same thing with microservices. Try to keep them as small as possible. One of the ways to think about microservices is from a business perspective. If 2 business concepts exist and are inexorably tied together, in other words, if one is down, the other one is useless, then those 2 are probably involved in a single microservice, right? And so I would encourage you to when you design your microservices, to think about things like that as well. Obviously, cluster your microservices for resilience. So you have one microservice, say it's a search engine or whatever, and you can have multiple instances running clustered for resilience across different regions or what have you. And the other thing that I often find is things like consistency or eventual consistency. How long is it going to take for me to get that update? And load times are determined by your SLA, not the engineer, right? So when people ask me that question, I say, well, what do you want? What does the business expect? You know, some things can be eventually consistent in a minute or 2. Other things have to be eventually consistent in milliseconds. So that's, you know, philosophically, that's how that stuff gets defined. And do things like use polyglot persistence. We're a strong believer in using the right tools for the right job. So one microservice might use a NoSQL database. Another microservice might use a relational database because it needs strong consistency, etc. We or I anyways, was kind of predisposed to, let's have one database that's clustered and everybody talks to it. And that's really not the best model. Even though it works relatively well, it is a single point of failure. So in designing microservices and looking at this idea of microservices being independent, not relying on one another, standing on their own in the event of failure, we realize a couple things. And this right here, I think, is one of the most important things when you move into distributed computing. And the idea is, regardless of the storage medium, our view of state is always of the past. So this is true with human beings. It's true with systems. When I receive a piece of information and I update my state internally, that is a historical current state. As far as I'm concerned, it's my reality, but something external to me may have changed and I just haven't received the information yet. And that becomes very important to understand. When you get into complex systems with time series data or bitemporal time series data where you have multiple points for the same point in time, this becomes incredibly important to understand. So you're basically dealing with a sliding window where now is in the middle. Depending on how far you go back, it could be minutes, days, weeks, whatever. That's all historical data. And going forward is all predictive data. And so as a reading comes in, whatever it may be, you're going to update the current reading, and it'll change from predictive to now. But you may also get a reading 2 minutes later, or maybe an hour later for that same point in time that you have to go back and update that. So these types of data structures can be complex, and it's very important to understand these ideas. So inside data, that's the data inside your microservice. That's your current present. That's your reality. That's what you know. Outside data that you're going to receive is historical. Once you receive it and process it, it is now historical, right? You don't know in that other service if that data has changed. And that's a very important idea to kind of wrestle with. And then when you ask a question, or you pull or push, or not push, but pull from another service, or another service pushes to you, then that is your hope for the future, right? Because you may not get it in distributed system because of latency and so forth. And then the last thing that we would say, as a result of these 3 first bullets, we say, hey, own your own data, okay? So what I mean by that is this design here on the left. We have a bunch of microservices. They could be running independently on their own JVMs, etc. However, they're all talking to a single database. If that database begins to experience problems or difficulties, then that's going to affect the entire application, right? Every service that you have. So a better design is the design on the right, where each microservice owns its own data in the appropriate persistence store that makes the most sense for it. So we have a payment database, we have a search cache, we have a product database. Now, one of the things that this implements or infers is you're going to have duplicate data, right? It just is what it is. We have duplicate data in our life. We file tax returns, and we determine what the government owes us, and then we find out that we actually owe them money, right? So, it is an eventually consistent model. Everything that we do is eventually consistent, yet in many ways we have a tendency to try to force some type of strong consistency in these types of systems, and it just doesn't work. So one of the ways to, I think, embrace this idea or this philosophy behind Reactive, something that we've been talking about, is the idea of promise theory. And promise theory is the notion that essentially you are going to declare your intent to the outside world, what your purpose is. And as a result, you will increase the recipient's certainty about your claim. And that claim could be related to past, present, or future. So the idea is I am not going to tie my behavior to someone else's performance. That's an obligation. If I have microservice A and I need something from microservice A in order to do my job in microservice B, that's a code smell. I have a problem, okay? Now, as time goes on, if microservice A doesn't work, my delta of error of what reality is will increase until microservice A comes back online. But I should be able to operate without impedance because microservice A isn't working for some reason. So I'm going to promise behavior. I'm not going to oblige someone else to perform for me. And then if there's something that I expect or something that I'm asking and I don't get it, my behavior has promised that I will work, and so therefore I have, in some other way, I have to take care of it, a backup plan or what have you. So some of the key concepts behind this is, as I had mentioned, think in promises, not obligations. Autonomy, right? Self-governance makes information local. You can't self-govern unless you have all the information that you need. If you need to rely on someone else for information, then you've now given up part of your governance. And as a result, it leads to a greater certainty and stability for your system. Okay? Autonomous services or services based on promise theory can only promise their own behavior. That's where they draw the line. They're responsible for their own behavior and actions. So when you build a system that is obligated, you diverge into an unpredictable outcome. From the beginning, you have a pretty defined beginning, but you have no idea if it's going to happen or not because you don't have control over the data or control over something. So you diverge into a decreased certainty of whether it's going to work. Whereas with promises, you kind of start with an unpredictable beginning. Yeah, I state what I'm going to do. I'm not quite sure how it's going to work out, but it will work out because I promise it will. And that leads me to something that gives me increased certainty. So these are ideas when you're building systems to think about. If you want your system to be successful, when I built our big system at Veridity, it ran for 2 years and never crashed a single time. It was on 32 JVMs, and I just stood back and was amazed because I built a lot of systems, and you know, you have problems. But we built everything isolated, bulkheaded. I'm sure you've heard all the terms, and it works very, very well. One of the things that helps with this is event sourcing, right? So we've heard of it before, I'm sure. Martin Fowler has a pretty good definition. Essentially, you're going to get in events or commands, really. You're going to process that command, and you're going to turn it into one or more events. And then that event is going to be stored. And it essentially gives you an audit record of behavior, right? As a result, we can adjust the state of our application retroactively. Not only that, we can go back and look at little time segments, and we'll talk about streaming. In many ways, it gives you kind of a streaming environment where you can set up synthetic boundaries, temporal boundaries within a particular sequence of events and run them and see what happens. This is very common when I was in the energy industry. This was a common thing that we did all the time. So some nice things about it is your storage system now becomes additive, which means it's very easy to shard, and there's generally a single key, right? So you're going to use a hash and distribute your data across your clustered store. The nice thing about that is these architectures distribute very well, as opposed to having some complex compound key. There's a lot less locks to deal with. You have a tendency to store current state in memory with these models anyway, so you don't have to hit a disk generally if somebody asks, you know, what is your current state? Also, as I had mentioned, in an event store, there's generally one key for an event, which could represent a significant amount of data. And criteria or behavior is tracked from the inception of the event stream. So I'll talk about CRUD here in a minute and one of the challenges behind it, but it kind of gives you this full view. So the granularity of your event model is going to give you, if it's real granular, you're going to have more control over analysis. If it's not very granular, then you're not going to have as much control. And the other thing is you can ask questions as the previous bullet from origin. So you don't have to worry about I implemented a new feature to track whether I deleted socks or not, right? It's just an event, delete, and you can track that from the beginning. And that leads to one of the greatest business values: you can answer questions not asked. And the extent of questions that you can answer is directly related to the granularity of your event model. It's a natural audit log. That was huge for me in the energy industry. When we worked with different energy companies and we worked with the government, everything had to be audited. They looked at our design. They're like, oh, okay, you got everything audited out of the box. And so this is your canonical example, right? A ledger. More mature business models use event sourcing in a lot of cases. Obviously, accounting has been around for a long, long time. And this represents debits and credits sequentially stored as events. And you're able to derive what your current balance is. So CRUD, something we're all very familiar with: create, read, update, and delete. They're actually events too. They're just not very granular. And the 4 different functions that we have in storing data, primarily in relational structures. What I really mean, though, is I'm talking about the notion of a relational current state model. So when you have a relational database, and I like relational theory, I think it's really neat, but we typically or generally store things as current state models. And I'll explain in a diagram what I mean in a minute. Before that, though, some of the things in CRUD is essentially you have this idea of representing change between 2 points. And that's basically referred to as a delta. In the energy industry, we have something called a SCADA system, and the SCADA system does something similar to this, but it does capture all the events in sequence. What it does for optimization is if the previous reading is the same as the current reading, it doesn't store the current reading. So the gap, where there's no reading stored, it's assumed that it's the value of the previous reading until that reading changes, then it'll store that. So it's a very efficient model. These deltas are implied inside the tool that you're using, such as an object, an ORM, and they manage all this for you. And essentially, they're going to save the state, they're going to calculate the differences to get the delta, and then they're going to update the backing model and flush that to the database. As a result, in this current state model, there is a side effect or something that occurs which is unfortunate, and that is essentially rather than tracking behavior or intent, which is what we're really interested in our applications, we're just storing data. We're updating the current state of the data. So we lose a significant amount of money, or not money, but data about our customers or whatever our system is doing. And auditing almost always is explicit. So if you are going to write something to an order line table and you need to audit it, you generally have to implement it. You either turn it on in a database, you write a trigger, you implement it in your ORM level, what have you. So this is our relational model. We have an order line table, a shipping table, and an order table. And right now we have 3 items. If a customer were to delete something before that order ships, then we would only have 2 items. And we would have no notion that an item was deleted unless we had implemented auditing. In an event-sourced model, that's automatic, right? Because it's just a sequence. It's an append of an event. And of course, shipping information, we're third normal form. All right, so the next topic, fast data. What is it? It's an interesting concept. Dean, our fast data guru, this is his definition. Data is processed as it arrives, leading to systems called fast data systems that ingest and process continuously data, and that can be done potentially for an infinite amount of time. So your fast data systems have a tendency to look something like this. And one of the things they're really good at is this notion of anomaly detection, which is fairly important. So fraud detection. Have you ever got a call from your credit card company or a text that says, hey, we suspect something is done wrong? Well, that's because they're processing the data and something tripped, an anomaly. And as a result, something tripped a violation, and as a result, they're going to text you or what have you. And so we have this idea. The issue, though, is a lot of times this notion of this type of system is completely separate from our regular microservice design. And, or even worse, we take a platform like this, like Kafka or Spark, and we say, well, it can do everything, right? It can store data for an unlimited amount of time. I can write SQL queries to access all my data. And we start to use a tool like that to build our application, what would normally be a microservice, and then we begin to run into problems because of performance, et cetera. So some of the ideas behind fast data is the boundaries, all right, whether you're processing real-time data or near real-time data, what those temporal boundaries are or how often it needs to be processed, again, are defined by the SLA. I think the most important thing is that we have a tendency to overlook is about streaming data is that the boundaries for a chunk of data inside a streaming model, they're synthetic. You set them. There is no beginning and end. If you're doing a batch, there's a beginning and end. You have a chunk of data. Or if you're doing, like traditional streaming of an image to a web page, yeah, there's a beginning and end. But in this type of scenario where you're constantly getting data in, you have to think a little bit different. So you're going to get a piece of the puzzle, right, at a moment in time, and you're going to have to reason about that. You're not going to have all the information. And as you get more and more information, the picture becomes more and more clear. That's a totally different way to think. Not something that I think, or at least I wasn't used to it, and it has implications on how you're designing your system. As I had mentioned, they could be potentially infinite, and also when you're dealing with streams, you have this new notion of this continuous flow. So there's typically maybe a sink and a source somewhere, and so back pressure should be part of the streaming library that you use. In the streaming world, reality is based on snapshots, right? You're going to take a snapshot of data, you have a synthetic beginning, synthetic end, and that's going to be your reality. That reality may be partial, and in fact, most cases it will be partial, but you have to know how to deal with that. And then to understand it, many of the streaming libraries are now providing more SQL-like commands, so doing things like group by and join in the context of streaming data are very popular operations. All right, so the last piece to our puzzle is feedback control, and this is the one I'm most interested in. Feedback control. So the idea is I want to constantly compare my system's actual behavior to its desired behavior. And as a result of that comparison, if the actual behavior differs from what the desired behavior is, then I'm going to take some corrective action. And I'm going to apply that corrective action to my system and counteract it. The result of that is going to be a deviation, right? And that deviation is then going to replace the deviation that occurred from this difference in behavior between desired and actual, okay? We do this all the time in exercise, right? We do an exercise. This is the behavior that I'm getting from it. This is the desired behavior, so therefore I'm going to modify my exercise and do something different. Again, all the things that we're talking about are what we do subconsciously every single day. Yet when we go to build systems, computer systems, we have a tendency to not do these types of things. So another nice thing about feedback controls, it can be very isolated. It doesn't have to understand the entire system. Again, functional programming, right? It does one thing. Same thing with feedback control. Feedback control could be very simple, like your thermostat in your house. You set a temperature to 78 degrees, it reads the temperature, it is not 78 degrees, it's 74 degrees, so internally it kicks the temperature up so it can catch up. Then it goes up to 75 degrees and it says, okay, too hot, tune it down to 73, it drops to 74, then the set point is equalized, basically. The idea of feedback control is very, very common in physical systems. Bringing it to the software world, though, is I think, paramount to things like machine learning and how we're going to reason about behavior, but it is a little bit more challenging than a physical system. Essentially, with feedback control, you're giving the idea of, I want to be able to nudge the system in a particular direction to more align actual with desired. They're self-correcting, right? And so the The idea is you have an external disturbance, and the feedback control or the feedback loop and control process is going to recognize that external disturbance, and it's going to essentially take a corrective action. And one of the things that you have to be careful of is not to overcorrect, right? So this is where data scientists come in, or engineers that really understand the process that they're doing. If you overcorrect, all kinds of things can happen. You could, if you overcorrect an energy, you can blow a transformer. There's a lot of things. So you have to understand, ultimately, what is your acceptable delta of error in the context that you're controlling. And essentially, as I had mentioned, they replace the deviation with another. So in computer science, however, it's a little bit different because the systems are less constrained. With a thermostat, it's very black and white, very well defined. It's the same thing with like building a bridge, right? In those types of engineering projects, they're constants: the river, weather, the materials, etc. In software, that's not the case, right? It evolves, it changes as we're designing a system. So we need to recognize that as we begin to implement these types of things. Another thing is when you're doing this, part of this is going to be anomaly detection. So the idea behind anomaly detection is, a lot of times what we'll do is we'll set thresholds, right? So for example, let's take an actor in ACA and say, if the actor's mailbox exceeds 500 messages, throw an alert. Well, the question I would ask you is, okay, is that really a problem though? If the actor mailbox does exceed 500 messages, for some systems that may be perfectly fine, right? For other systems it may not. So thresholds are kind of misleading, right? They can cause alert fatigue and other things that can be problematic. So we have to be careful of that. So anomaly detection is, hey, I have a whole bunch of data here. All of it looks strange. Let's apply some type of corrective algorithm to it or smoothing algorithm to it. And as a result, we can essentially figure out what the correct value should be. Or it could be an outlier, right? In our industry, we would get readings that would jump, that would spike. And that could cost the customer a lot of money. So we applied an anomaly detection algorithm to it, and in most cases it was just an erroneous point. And we would adjust it in line, and that's where smoothing algorithms come in, right? As you receive your data, you're going to take a look at it, again, in that temporal window, the synthetic boundaries, and you're going to make some decisions about it, on how you're going to process it, what you're going to do, and so forth. And then, obviously, this is one of the most important things in this, is you're going to train your model. Whatever your model is that's implementing feedback control or machine learning, you need to train it with historical data. And as it trains, it will get better and better, and or at least in theory, it'll get better and provide better results. So your typical canonical example here is this. You have a disturbance. It comes into the system as an input. The system has a status, sends it to basically a measuring element that is going to implement feedback. It is then going to access a set point, and it's either going to increase it or decrease it, whatever that means in your system. It doesn't necessarily have to be, add one to an integer, decrease, whatever. And as a result, it's going to generate this error. The controller is then going to create a command and send it back to what we're calling an effector, and the effector is going to implement control. That feedback is then going to go all the way back up to our entrance, and they're going to do it again and again and again, right? And that's the notion of this. Dean uses a great point in his book about this. So, all right, I want to running behind a little bit, so I'm just going to go a little bit faster. We have all these things that we're talking about. So now we're going to talk about building systems. Now that we have this information, how do we do it? So you'll recall in microservices, we talked about these different aspects that become important, right? We're familiar with them: own your own data, polyglot persistence, etc. So we start with a microservice. So this would be our first design. So we have these microservices, they have their own data, okay? Now, we have this notion of when do we use CRUD. So If you care about history, use event sourcing. If you care about auditing, event sourcing. If you're going to shard your data, event sourcing. If you need strong consistency, right, CRUD may be a good version or a relational model. If you don't care about current state, and I've seen many applications that really don't care, then CRUD's a perfect example as long as, you know, availability isn't a big issue. So now we've implemented these ideas. So in our search cache, that's a CRUD-based, we're just updating it. And in our other two microservices, we have a payment database with NoSQL and event sourcing, etc. So now fast data, right? Again, we went over these things. The one thing about fast data is we need to understand it's based on streaming. We have these synthetic boundaries, and fast data should be orthogonal to our microservice. And I'll show you that in this design. Not to say that you can't have streaming within a microservice and you can call it fast data, but as a result, one of the ways that we project this or say you should do it is by making it orthogonal. And one thing you should remember, fast data isn't necessarily a historical persistent store. That's not what it was designed for. So I like to think of it this way. Our data backplane is our fast data. It can be Kafka, whatever. Around it, we have all these little microservices that are self-governing and have their own rule. They all pull from this central stream, and then they modify the data or do whatever they got to do to it to make it applicable to their context. So in a design, we would have something like this. We have our microservices, and we have our data backplane. So now we're going to implement feedback control. Again, we talked about the different aspects of feedback control and how we want to do that. Everybody recognize this? Supervisory control in ACA, that's feedback control, right? You have implemented push-based feedback control. Push from the child to the supervisor. In bigger applications, we can pull it off to the right and we can implement it through things like Neroff, RapidMiner, and Spark, machine learning libraries, etc. All right, so we're almost there, but we're missing one thing. And what we're missing is insight. And this is kind of like a whole system, right? We have our fast data, we have our data backplane, we have our persistent storage, we have mechanisms for capturing data in regards to Insight Elasticsearch, etc. We can visualize it with Grafana or Kibana, etc. And now we have not only a system that's reactive with all these components we've been talking about, but it also is monitored. You have insight into what's going on. So in Insight, you know, instrumentation is should be a local aggregation of events, which then gets passed out into some collector, collectee. Collection can be, again, a local registry for optimization. And then aggregation, you can dump it into a Kafka cluster. And the last couple notions are storage. You can use, as we saw there, Elasticsearch for events, Cassandra time series database for metrics, Spark for analytics, Riemann for notifications, and Grafana and Kibana for exploration and data discovery. So if you're familiar with those tools. Okay, so that's it. I want to open up for questions for anybody, or you can come up afterwards. So, thank you.